Now that we've completed our circuit, we have a transmission line with a load at one end and a source at the other. And again, bear in mind that this load is not just a physical, resistor inductor element that's placed there at the end. This load, ZL, is the equivalent circuit for some more useful circuit. The ZL is an input impedance to some useful microwave device. Almost certainly that's here. Likewise, the same thing on the other end. The source is not simply an ideal source with some element attached to it in series. This is an equivalent circuit to some useful microwave device that is supplying energy into our system, into the transmission line, and ultimately absorbed by the load. So let's look at that. Now that we have a full circuit, we went through and we resolved our ambiguity previously with respect to our complex wave amplitudes, and we have an unambiguous expression for current and voltage. Now let's go back and look at energy, power flow, the rate of which energy flows along our transmission line, energy flow, and the rate of that energy flow. Now, the first thing we bear in mind is there is a power that is delivered from the source. The source delivers energy at a certain rate. We call this delivered power, and so we can think of this the rate of energy flowing out of our source. Likewise, on the other side, there is a power that we define as the absorbed power. This is the rate at which energy is flowing into the load, being absorbed by the load. Now, between this source and this load, we have a two-port device, which is a lossless transmission line. And the fact that it's lossless is the most important fact here, because if that two-port device is lossless, it cannot alter the rate of energy flow. The delivered power must be equal to the absorbed power if the transmission line is lossless, and we assume that it is. And this is again true for any two-port device that is lossless. A two-port device that is lossy will reduce the rate of energy flow from delivered to absorbed. The absorbed will be less than delivered. An active device can increase the rate of energy flow. The power absorbed can be larger than that delivered by the source. But if we have a lossless device, then a passive lossless device like a transmission line, then the rate at which energy flows into that two-port device will be equal to the rate at which the power or energy flows out of that two-port device by conservation of energy. And that's certainly the case that we have here. Now, in addition to those two powers that we just discussed, the delivered power from the source and the power absorbed by the load, there are two more power values that we've talked about associated with the circuit, and that is the power flow associated with each of the two propagating waves along the transmission line. So these are the third and fourth power values we're going to concern ourselves with. The third one being the incident power, the power associated with the plus wave propagating down toward the load. This wave is, we say, incident on the load at this end. Then we have a minus wave that propagates away from the load back toward the source. There is a rate of power flow, rate of energy flow, I should say, associated with that wave as well. This minus wave power is what we call the reflected wave power, the wave that's quote-unquote reflected from the load. So the incident plus wave power, plus wave propagates down toward this load and then is reflected from the load, and then we have a minus wave or reflected wave propagating back in the other direction, and each of those two waves have an energy rate associated with them, a power associated with them. And so if incident power and reflected power, and the incident power and reflected power, of course, are related by the magnitude squared of this load reflection coefficient. And that load reflection coefficient, the magnitude, can have any value between 0 and 1. And so this magnitude squared essentially tells us the percentage of the incident power that is reflected. If the magnitude squared of gamma L is equal to 0.36, that means 36% of the incident power will be reflected. If it's 0.73, then 73% of the incident power then will be reflected. So the magnitude squared of gamma L will tell us directly the percentage or proportion of the incident wave that will be turned around and reflected. The Question then is, how are these four power values related to each other? The important thing to understand here with respect to this particular circuit and how we've defined it, that each of these four values must be positive. They cannot be negative. Specifically, we find that the reflected power must be less than the incident power if this load is passive. We are assuming that this load is a passive load. The reflection power could be equal to the incident power, but it could never exceed it. And therefore, when we take the difference of these two powers, we get what we call a net power flow, and that must be a non-negative value. Its smallest value could be 0, but otherwise it must be positive. This is the difference between the rate at which energy is flowing, energy associated with the plus wave, minus, or the incident wave, minus the rate at which energy is flowing that is associated with the reflected wave, or the minus wave. Again, those two are the net power flow along our transmission line. And the important thing to remember is that net power flow is the same at every location on the line. The net power flow at the beginning of the line is the same as the net power flow at the end of the line. And that's due to the fact that the transmission line is a lossless device, and therefore it cannot alter the rate of net power flow. Again, this value is a net power flow is a non-negative value. It must be greater than or equal to 0. Now, think about what that means with respect to the incident power. The net power flow is equal to the difference between the incident and the reflected. Again, both the incident and reflected are positive values. The reflected must be less than or equal to the incident, so the net power flow is a positive value. And because of that, we can take this equation and rewrite it, or take this equation rather, and rewrite it in terms of the incident power. The incident power is equal to the net power flow along the transmission line plus the reflected power. All right, stop and think about that. That comes directly from this result here. And because each of these are positive, the reflected and the net must be at least non-negative, 0 or positive, we find that the incident power must be greater than the net power flow. Likewise, we know that the incident power is greater than the reflected power flow. When I say greater than, I mean greater than or equal to. And so again, because all these are positive, the incident is the largest, generally speaking, of the three values. The incident, the net, and the reflected. The incident is going to be the one that is larger than, or at the worst case, equal to the other two. So let's do another boundary condition analysis for this circuit. But in this case, we're going to do a boundary condition analysis based on energy flow, on power. The criteria we're going to use to apply the boundary condition is not going to be KVL or KCL or any of the other circuit boundary conditions we used prior. In this case, our boundary condition that we're going to use is conservation of energy. So we're going to start with the fact that the difference between the incident power and the reflected power along our transmission line is our net power by definition, and that value is invariant with respect to position. It does not change as we move along the line. The net power at the beginning of the line is the same as the net power flow at the or energy flow at the end of the line. So let's go back to the beginning of the line. And so we find the net flow of energy, the rate of energy flow here is, let's say, 23 millijoules per second, for example. Well, where does that energy coming from? By conservation of energy, it must be coming from somewhere. And of course, it is coming from the source. If we have at the beginning of our transmission line energy passing that location at a rate of 23 millijoules every second, it must mean that the source is delivering that energy at that rate. And so by conservation of energy, we find that the power delivered by our source must be equal to the net power at the beginning of the transmission line. And the net power at the beginning of the transmission line, of course, is equal to the difference between the incident and reflected power. Once again, all of these values, power values, must be positive. If we have an active source here and a passive load here, how we've defined them, they will all be positive, or at the very least non-negative. They could be 0. And so we find that the delivered power is equal to the difference between the incident and reflected power, just as the net power is equal to the difference between the two, meaning, of course, the delivered power is the net power by our conservation of energy argument. Once again, the important thing to think about here is the relationship in terms of the size of each of these values. Because they're all positive, the incident power is going to be the greatest of those four powers in this equation. The incident is going to be greater than equal to the reflection coefficient, or the reflected power, rather, as we know. And it's going to be greater than or equal to the net power, as we know. But now, because of this boundary condition, this conservation of energy, we notice that the incident power is likewise going to be greater than equal to the power delivered from the source. All right, the incident power is greater than or equal to the power delivered from the source, and that's a very important statement, and one that you need to think about, because a lot of students will get this wrong because it seems non-intuitive to them that the incident power is due to the source. And because the incident power is due to the source, then the incident power must be equal to the power delivered by the source. But remember, there are two terms with respect to the plus wave propagating away from the source. There were two terms in that solution. One had to do with the source, and certainly that does contribute to the power of the incident wave. The power delivered contributes to the incident wave power, but there's also a second term which is due to the load itself. We had a reflected wave that comes back and reflects off the source and adds to that incident power. And so the incident power is going to be actually greater than or equal to the power delivered by the source, not equal to, greater than or equal to. Again, that's very important that you put that in your mind, because students make that mistake frequently. All right, one last boundary condition, and we're going to apply that at the end of our transmission line where the load is attached. And again, we know the net power flow at the end of the line here is simply the difference between the incident and reflected power. But by conservation of energy, the rate at which energy is flowing out of our transmission line must be equal to the rate of energy at which energy is flowing into our load, the rate at which the energy is being absorbed by the load. And so we can come to the conclusion that the absorbed power is equal to the net power flow, the difference between the incident and reflected power. And because the delivered power is equal to the net power and the absorbed power is equal to the net power, then in fact the delivered power must be equal to the absorbed power. And all of that is basically reflected in this equation here. Now, the fact that the delivered power and the absorbed power are equal to each other, it works out that way, but it must work out that way. We know that the delivered power and the absorbed power must be equal, since this transmission line is a two-port lossless device. So this all works out. The important thing, again, or one of the important things to really take away from this equation, again, all four of these values are positive, which means of the four, the incident is going to be, generally speaking, the largest. The incident power is going to be greater than equal to the reflected power. It's going to be greater than or equal to the delivered power from the source, and it's going to be greater than or equal to the absorbed power at the load. The incident power is the emperor of all powers, as it were. It is the one that is likely to be the largest, or at the very least as large as any of the other powers. I want to emphasize once again this result, the fact that the incident power along our transmission line, the power associated with the plus wave propagating from the source to the load, is actually going to be greater than or equal to the power delivered from the source. And again, as I stated earlier, oftentimes students and engineers sort of incorrectly think that the incident power is going to be equal to the power delivered from the source, but that's simply not the case. Again, that plus wave propagating from the source down to load, as we tried to show in the analysis in the boundary condition, has two terms. One term which is dependent on the source, but the other one which is dependent on interaction of the reflected wave with the source itself. The reflected wave effectively gets bounced, reflected again from the source. And so there's two components to that plus wave, and the source is only is only one of them. So bear that in mind. And the math, again, very shows that clearly. If we look at the delivered power, the reflected power, the power that is the largest of the two almost certainly is that incident power. Again, at the very least, the incident power is going to be equal to one or the other of these values. Perhaps this will help you see this. If we go through and say that the power delivered by the source is equal to the difference between the incident and reflected power, the net power, we know the reflected power, of course, is dependent on the, or the value of the reflected power is determined by the magnitude squared of our load reflection coefficient. And so the reflected power is the magnitude of gamma L squared times the incident power. And so algebraically, we can rewrite it in this form. Remember, the magnitude squared of gamma L is a value that is going to be between 0 and 1. And so this term here is likely to be between 0 and 1 as well, meaning the delivered power is going to be some fraction of the incident power. And so we go back again. If gamma L squared is equal to, let's say, 0.25, that means 25% of the incident power is reflected. That likewise means that 75% of the incident power is equal to the delivered power. And so we can go through and take the incident power and parse it into two parts. The part that is reflected, and the other part then is the power that is delivered by the source. The delivered power plus the reflected power is equal to that incident power. And because of that, we have an incident power that generally is the largest of all of those values. Summarizing, therefore, these ideas in the most blunt way possible, what I want to take away from this, if nothing else, is this relationship here. This is our power relationship or conservation of energy. The delivered power is equal to the net power, which is the difference between the incident and reflected, and the net power is equal to the absorbed power, again, because we have a lossless transmission line. All four of these values are positive, and mathematically that means that the incident power is going to be greater than or equal to delivered power. And of course that means likewise the incident power is going to be greater than or equal to the absorbed power, and likewise greater than or equal to the reflected power. The incident power is greater than or equal to all of the three other powers described in this equation.